I would like to invite Jaidev Deshpande on the stage for the session. He is a full stack data scientist who specializes in building ML and AI products. And today he will be speaking on relearning Python with 10K Novices. So, Jaidev, please take over.
I trust I'm audible. Okay. Thank you. Uh, so over the last 3 years, I have been very deeply involved in what I can only describe as perhaps the most diverse or the most extensive experiment in mass education. So this is what is known as the IIT Madras program in data science and applications. And what they decided to do 3 years ago, 4 years ago in fact, was to create a bachelor's degree program in data sciences and applications and let people in without a JE. So at that time, I was teaching pretty much foundational machine learning at various places, and I was sort of very curious as to what sort of content they are coming up with. First of all, many people in the edtech industry were shocked at this because why would an IIT just let people in without the JE? That was a big shock, and I thought maybe I could just go in for a term, take a look at what kind of content they have in maths and statistics, see if I could perhaps learn something from it. But within the first 6 months, I got really addicted to the program, and you'll see why. It's easily the most diverse MOOC in the world. The youngest of our students is 17 years old, and the oldest of our students is in their early 80s. There are people from various socio-economic backgrounds in the program, and we also perhaps boast a better gender ratio than most other engineering schools in the whole country. And oh, by the way, I'm going to be using the pronoun we to refer to we, the program, as well as we, the Python community. But the opinions are more or less solely mine as an analyst. So this is what happened eventually. Okay. Yeah. Um, there is this concept called the Pons asinorum, which is colloquially, which translates into the bridge of asses. And this is essentially the isosceles triangle theorem from Euclid's Elements, and it's the theorem that we all know well, that if two sides of a triangle are congruent, then the angles that are opposite to them are also congruent, right? And in the medieval ages, what people started realizing during the Enlightenment is that if somebody could prove this theorem based on exactly what they had learned from Euclid's Elements before that, the axioms and the theorems that had been proved up to this point, if using just that and nothing else, people could prove this, then they would probably go on to become above average geometers. And anybody else who could not was sort of doomed to being an amateur or a barely above average geometer, right? And so during the Enlightenment, the Pons asinorum became, you know, the colloquial term for describing simply a academic filter, right? And in our course, the Pons asinorum is, guess what? Introduction to Python. It is the single largest place where people fall off. And we tried to see why, and that's what broadly the talk is about. So this is broadly what the timeline, or not the timeline, but the volume of the program looks like. 36,000 people so far have entered the program in the last 4 years. Of which, and this, by the way, Foundation 1 is the first semester of the program, the first 6 months. And it's a self-paced program. You can take your time and do it whenever you like, right? 36,000 people enter the program. Only 26,000 of them have actually entered the second semester. So we're down to 70%. The next year is called the diploma level, where you get to earn 2 diplomas. From these 26,000 students, we are down to 10,000 students. So out of the 36,000 that entered, only about 27% are at the diploma level. The degree level, this is where you actually exit the program, finally, is only 650 students right now. That's 2%. And the number of people who have actually exited with degrees from the program is just nearly 100, 0.2%, or maybe less, in fact. I've rounded the figures up a little bit. So there was some criticism as to, what would happen to the brand if you just let people in without the JEE. So what they have actually very smartly done is that they have flipped the funnel. They let everybody in, more or less, but getting out is difficult. It's almost impossible. It's like instead of having the filter over here, the JEE filter over here, they have made the exit difficult. And so we take everybody in and we like ruthlessly eliminate people until only the best are left. So that's broadly the idea. And the problem with this big gap that you see here, 100, only a quarter of the people are even getting diplomas. The problem there is the Python course. In the second semester, we have a course called Introduction to Python, which is a 6-month long course, which obviously you need to be good at Python, otherwise there's no hope that you will be able to do anything reasonably in web applications or in data science particularly. So we need people to be good at Python. And a quarter of these people are stuck. That is the scale and the size of the problem. And it turns out that every third student basically fails in Python, the way we have seen it. So here you see that the number of attempts that people give is on the x-axis. The scores they receive out of 100 are on the y-axis. You need to pass at 40. And the size of each circle represents how many people are stuck at that position. And you'll see something very peculiar here. Every vertical bar sort of looks like a dumbbell, right? There are big circles at the top and the bottom, which means that as proud as we are that there are a lot of people who are scoring a perfect 100, we're just as embarrassed that there are equally many people who are scoring an exact 0, not failing, but scoring a 0. And this is just inexplicable. There's actually no explanation for this sort of an effect. And you see that the circles just get smaller and smaller the more attempts people take. So people are just giving up after a couple of attempts. And what we want to really do is at least save these 20% people. The people who fail in the first and the second attempts. By the time they give the third attempt, we want to make them pass. So then we try to decide what could be the best, most relevant interventions that we could do in order to scoop these people out of at least this quarter. And this is the most sizable chunk of students that could relatively easily pass. Of course, there's not much that we can do around this area, because by the time you're 7 attempts into the course, you have already been there 3 years, and yeah, if you can't finish Python in 3 years, then you're probably already left, or sad as it is, there's not much we can do to help. So this is what we tried looking at first. What is it that explains, programming performance? What do people's grades really tell us in Python and in some of the other subjects? So this is what the course broadly looks like. It's a 12-week course with a quiz at the end of the first 4 weeks. This is an MCQ quiz. Another quiz at the end of the first 8 weeks, and then there's a final exam at the end of 12 weeks. But the trouble is, and people do very well in these quizzes, by the way. The trouble is that there are 2 programming exams at the end of 6 and 10 weeks respectively, out of which 1 you need to pass. So while people are great at answering MCQs about Python code, reading Python code, interpreting it, answering sort of elementary questions about data structures and standard library and so on, syntax related stuff, they're actually pretty bad at practicing coding. So when it comes to converting your logic into an algorithm and typing it down, that's where people really fall off. And again, keep in mind that these are people from as broad a background as you can imagine. There are people who have never seen a computer in their lives. Right? So one of the things that we did for some of the other courses was every week has a practice and a graded assignment. So if you were to take the scores of all the graded and practice assignments in the first 4 weeks and try to predict how much a student will score in quiz 1, that's a regression, right? Then you try to do the same for quiz 2. That's another regression. And of course, you could take 6 weeks worth of scores, try to predict the scores in the programming exam. Python is the only course where the regression fails, and badly. In pretty much every other course, if I were to feed your scores from the first 4 weeks, 8 weeks, and for all the 12 weeks respectively into my model, with a fair amount of confidence, I can tell you how much you're going to score, what's your grade going to be at the end of the course. Python is the only place where that doesn't work. And that is because, we have weekly deadlines and all, people get desperate, they might collaborate, copy answers and stuff like that. GPT is one big, I wouldn't say problem, but it is certainly something that we have to deal with. So when it comes to submitting weekly assignments and homework, people are just desperate, and and by the way, I have been guilty of that as well. I have been, chasing deadlines. Okay, I just need to meet this midnight deadline. I need to solve these 5 questions. I swear I'll study tomorrow. So that's what happens to me once in a while in some subject or the other. But the trouble is that, finally when you end up in the programming exam, there's no way that you can, look up anything at all. Of course, if there's something very specific that the problem needs, then the documentation is provided alongside the question itself, like some specific function that comes from the standard library. You might need to use something like functools to solve this, and the documentation is given. Right? Nevertheless, Python is by far the only course that completely fails to be predictable. There's no explanation for why people who score well in Python and why they fail, essentially. Right? This is a global thing, really. It's not really specific to this particular problem. There are studies which show that if you look at a general audience all over the globe, the typical undergrad introductory programming course takes somebody 5 to 6 attempts to clear. By comparison, the second most difficult undergrad course is multivariate calculus and linear algebra, which takes about 4 attempts to clear. And this again is assuming people who don't have a technical background, people who did not do sciences in their 12th and so on, right? So it's a global phenomenon. We know that this problem exists. We are not necessarily good at, solving this problem any more than we were, say, 15 years ago or so, right? But the flip side of the situation also is that most good programmers have actually never taken a course. So there are a lot of good programmers who have not taken a course, and people who are taking a course aren't getting good. So where's the balance? That's actually the question that we are trying to find out. This is the pattern that you see in programming grades is something that you see in high school mathematics as well. Programming, like maths, is perfectly bimodal. Some people just get it and others don't. Right? This is something that came from a study that Anand did with the Tamil Nadu CBSE, was it? State board. Yeah. What explains people's marks, essentially? And it turns out that, this is the mathematics part. You see that there is a spike at 100 and there is a spike at 40. Now we can explain what the spike at 40 is, but why is it that more people are scoring 100 than 99? That's, maybe the theory goes that the examiners of mathematics courses can defend their grades in the sense that it's an objective subject. I know exactly that the paper was perfect, so I can choose to sort of award 10% marks to a particular student for a given question, right? And that's exactly what we see here too. You see those dumbbell sort of structure that is going around in all levels. Many number of people scoring perfect zeros, many number of people scoring perfect hundreds, and the middle is somewhat flat. There is no explanation for this effect, as I said. It has been studied fairly, and people have tried to explain it with various parameters like background, ethnicity, gender, race. Nothing really works. There's no explanation for that effect. So then we tried to look at what other subjects are correlated with Python performance. And in the first 6 months in the foundation 1 term, these are the 7 subjects we roughly studied. There is English, there is 2 levels of English, there are 2 levels of maths, 2 levels of stats, and there is a precursor to Python called computational thinking. Can anybody guess which subjects Python corresponds to the best? Exactly. So it corresponds very well to English, corresponds very well to Maths 1, but not Maths 2, because Maths 1 is all about primary calculus, polynomials, and vectors. The kind of stuff that you can do reasonably well in Jupyter Notebook. English is obviously, because reading comprehension is a big deal, and when you start learning Python, the very first few things that are given to you as practice problems are word problems, right? Stats 1 was simply counting stuff for which you didn't really need, much more than a scientific calculator really. Stats 2, however, was slightly higher order statistics. And the person who taught Stats 2 actually encouraged us to go and try do stuff in scipy.stats and stuff. So that gives a little bit of a boost, right? And after we saw this pattern, we actually went around talking to people. We tried to gather some anecdotal evidence, some quantitative results of what explains people's marks in Python. And this is the one big lesson that we really found. And most people dislike programming, but some people may grow to love it. People who would otherwise hate doing Python exercises, they loved it when they were doing stats, right? And retrospectively came back to Python and started getting better at Python, right? So what should people do, right? And again, from the surveys, what we find out that obviously we know that mathematics is highly synergistic with programming, but the finding here was that synergy lies in broadly three buckets. One is where programming helps your math comprehension, and it also goes the other way, that your math comprehension helps you write better programs. And then there is a third middle ground where you say that, okay, my mathematical results are so absurd or so counterintuitive that I have no choice but to actually write a piece of code to test it out, right? And let's talk about examples of these. So for example, an example of programming helping math comprehension is polynomials. Polynomials are notoriously difficult to factorize if they're not quadratic. There's no general rule, right? But they're trivial to plot. So if I have some idea about where a root or an extrema may be, I could of course do it analytically and figure it out, but to see whether my analysis is correct or not takes me exactly 3 lines of Python code. That's very easy, right? The other aspect of it, the reverse aspect, is that mathematics helps me put bounds on my programs. So there was an exercise where we had to generate a simply connected random graph. And as expected, most novices, what they would try to do is, I know the number of nodes, I'm going to pick a pair out of them at random and just start dropping edges at random until eventually the graph gets connected, which actually works for a small enough number of nodes. But when they realize that there is something called the handshake lemma, so there needs to be a relationship between the number of edges and the number of nodes, which if violated could lead to over-connected graphs or under-connected graphs. The moment they realize that, the code becomes a lot more structured and smaller, in fact. You're not doing things like while true, keep on dropping edges until the graph is connected. You're being very careful, very mathematical about it, right? So this is an example of how math helps you structure your code better. And then the third is clearly, some results are so ridiculous that you have to write code in order to really realize that your analysis was correct. So either your analysis has to be correct or your simulations have to be correct. If both are wrong, then you're in trouble. One example of this is obviously the Monty-Hall problem. And there's clearly a problem in this code because the odds of winning a car after you switch the door is 0.66, it's not 0.5. I clearly made a mistake there. But there it is. So this is essentially the summary of lesson number 1, that we need to introduce programming in non-programming courses wherever possible. Right? See if you can encourage students to do pretty much every problem with Python, of course, with the warning that they may not have access to a Python interpreter while they are appearing for the exam, but they can at least rest easy about whether they have understood concepts or not. Right? Programming as a learning aid, so to speak. The next bucket of analysis, what kind of code do people write? This was what we saw so far was how well their grades correspond with other subjects. But in Python itself, what kind of code do people write? So what we did was we took all the snippets of the code that was submitted during the programming exams and we did a little bit of cleaning on them. We threw it into an LLM, got the embeddings and tried to cluster them. And these are broadly the kind of clusters that show up amongst the people who fail Python. At the very top, in the 35 to 40% range, again, remember that 40% is what you need to pass, just the quote-unquote creamy layer of the failures. This is what we found. Most of those are simply incomplete solutions. People get kicked out of the portal because time is up. But till then, they are writing perfectly reasonable code. With just a little more time, they could have, passed, perhaps, right? They are very legit. The prefix, if you read the code from left to right, you see that, okay, the logic is sound, people are moving in the right direction. So there are a fair amount of people failing, in fact, quite 5% or so, because time is a problem. How do you fix that? Practice, right? The next tier is simply, inelegant code, like tons and tons of nested loops and, dictionaries where they are not needed, far too much hard coding, creating lookup tables for no reason, that sort of stuff. And the other big category there was straight up syntax errors. Why would people even write code that have syntax errors? Early on we realized that one of the reasons why this was happening was that the portal that we were using, people couldn't exactly tell the difference between a syntax error and standard output or standard error. So we had to fix that, and people got slightly better at reading or even detecting the fact that code is simply crashing and not running, right? So this is where they are. The next year is simply silly mistakes. Lack of conceptual clarity about Python. Lots of people get confused between printing something and returning something. Lots of people get confused between the way to write a set and the way to write a dictionary. You intend to write a dictionary, you end up writing a set. And then there are, mistakes like, I've seen one pattern that occurs very frequently is mylist equal to mylist dot append something. So basic data structures, their understanding obviously, but again, I can't create a week's worth of curriculum, say this week we are going to learn lists. Or let's start our Python course by sorting a set of integers. That is really boring, and that doesn't work. People are going to be bored on day one, and that's not how you learn data structures at all in the first place. But when they do, this is the sort of thing that happens, right? And then finally, the bottom tier is people panicking and giving up. And how do you see that through code? The people who give up, that big zero ball that you saw, is simply empty snippets, just white space, nothing else. In some cases, we have a template like finish the following function. There's the header of the function with a docstring, and there's nothing below the docstring. People choose not to write anything below the docstring. And this, we also have a proctoring software which actually captures people's faces and the screens while they are taking the exam. Some people just go to sleep during the exam. And then the proctor has to wake them up. Your face needs to be seen. And if you want to sleep, just lie back on your chair and sleep like that. Do not put your head down. So those sort of things started happening. And people just, when it's their second or third attempt, they either don't show up, in which case their grades are just NA, they're not counted. And when they do, they just give up. Even the panic and desperation part of it is a little interesting because you can see the way the code evolves. Like the code is time-stamped. It gets auto-saved every few minutes until it is actually submitted by the students. And typically for a good student, what you'd see is a nice logical progression of the code. They are, writing a few lines, going back a couple of lines, rewriting them, renaming variables, figuring out that there's a silly mistake, and then, fixing that. But the people who panic, it's like every timestamp of the code that you see, it's a entirely different problem that they're solving. I would have maybe 10 lines of hard-coded solution in a moment and a tiny function call in the next. So I've deleted that whole thing and written one nice line. And obviously both are wrong because the problem is asking for something else entirely, but you can see people panicking. It's not pretty at all. So that's lesson number 2. We know that practice makes perfect, but we have no clue how to get people to make the time to practice more. And here I'd like to do hat tip to Greg Wilson, who did this beautiful talk at Sci-Fi 2014 on the lessons that he learned from running software carpentry for about a decade. And he also came to a very similar situation. He had a similar problem. Every curriculum in the world, every academic committee agrees that programming should be a part of the curriculum. What they can't agree on is what to take away from the curriculum to make room for programming. Because obviously everything else is just as important, but you need time, you need patience. People need to make time to practice programming. That can't happen through simple pedagogy. Right? The third and the last bucket of analysis that we did, we have a thriving discussion forum. We use a discourse instance. There are thousands and thousands of students on it and so on. What do people talk about when they talk about Python code? 5,000 threads or so in the last 3 years with about 200,000 individual posts. The most common threads, again, similar kind of clustering techniques. We scrape the posts, throw into an LLM, get the embeddings, and try to cluster the embeddings to see if we can read some sort of clusters from them. The most common posts are about grade anxiety. I appeared for my exam yesterday. My marks are not out yet. I'm really scared. When will the marks be out? Why did I score a B? And so on. The second most common, again, is simply screenshots of code or syntax errors or something or the other. And a single line question, why doesn't this work? Now, what troubles me the most about this is that we, as the community, have known for ages that this is the worst possible way of asking a question in any public forum. In fact, the way that even I learned about all of this is from Anand's talk at PyCon Pune 2011 on how to use the in PyCon mailing list properly. Do not put screenshots. And of course, Kushal Das and Shaktiman have spent pretty much their entire lives, nicely prodding people and getting them to learn the etiquettes of mailing lists. Stack Overflow people know this very well. They'll tear you apart if you do stuff like that there. So, and here's the thing, we accidentally did this experiment once where, well, the experiment wasn't accidental, but perhaps a slightly misguided experiment where we, correct me if I'm wrong, Srinivas, we started giving people some sort of credit for their time on discourse. So there were a ton of people going around answering those questions too. Not one of them actually bothered to correct, the OP in the sense that, please don't put screenshots because who was going to be searching this has to look at your screenshot and Google. Instead, at least put markdown formatted code. You don't know how markdown works? Take a look at this. This is a guide, right? So we didn't do that, and that sort of just blew over. We probably need to go and start putting in. We've started, right? Like we've started correcting things there. But the fact that this gobbles up a big chunk of the discourse, quote unquote, is problematic. Again, the same thing. Screenshots of questions that are asked in MCQs with a single line caption. I don't understand the question. Or it doesn't work. You need to at least tell me what you have tried to do in order to, for me to start helping you. I need to figure out where to start. I can't start writing an entire thesis there. Right? This is something that we have known for a long time. Most rare and actually the stuff that help, only 5% of the posts are specific and pertinent questions about a very particular problem. They tend to be about matrices sorting file IO because that's what's in the curriculum. But these are actually pertinent questions. Like I tried to, matrices by the way here are just lists of lists. I tried to modify some particular row or something. Or I tried to use a list comprehension to create a matrix. I modify one particular element of it. Why is the whole matrix corrupted now, right? So then you bring in things like copy by value, copy by reference. So that's actually a good way of starting a discussion about data structures, right? You do not start by telling people what a list is. You say that, okay, I have got an image, I probably have an image or an audio file or something which is an array or a matrix, and then I start manipulating it because then, people come back to data structures eventually. So that's the third lesson. Good code is about good communication. Again, we always knew this, but the takeaway here is that I've had my, share of teams thinking that good communication is a luxury they can't afford. And now I can go back to them and say that, bad communication helps even novices. Sorry, it hurts even novices. So you're not, it's not beneath you to communicate better in any sort of a setting. Clear, good communication leads to clear and good code, obviously. So finally, this is the summary. We are desperate. We need the help we can get. If you are somebody who's interested in mentoring us or coming out and talking to our students, more than welcome. Volunteers are welcome. And by the way, I don't mean, by volunteers, I don't mean that you have to work for free. If you are speakers, especially from the industry, please come and talk to our students because they'll listen to industry speakers, they won't listen to us, right? And keep in mind that these are a bunch of kids who really want jobs. So that's actually our biggest audience really right now, right? If you can, please outsource some of your work to us. To see, there are some success stories that we have as well. We have had pretty end-to-end extensive application development projects that have been, pretty well appreciated. You can help us conduct vivas. You can help us conduct interviews. And, just come and talk to our students. Share your programming journey. There are tons of people here who are not trained programmers. But they are, in fact, I would say that the best Pythonistas I know are not computer science people at all. So please come and talk to us. You can reach out to me there. Thank you.